It's time to move on to another section of our course. This time we're going to talk about arrays and structs, namely how we represent some more interesting data structures in our memory. So we're going to move beyond just simple integers and floats and characters, but talk about arrays of values and complex structures that involve multiple elements. That's what we call structs in the C language. Okay, so to outline this section, we're going to start off on arrays and how we access them in memory, the various elements of the arrays, and then we'll talk about multidimensional arrays as well as multi-level arrays and the differences between the two. Then we'll move on to talk about other kinds of data structures in memory and how they're aligned to the appropriate addresses to optimize memory access. Okay, so let's get started. We'll begin with arrays, and the basic idea behind arrays is that they have elements of a certain type, in this case using the T. Of course, the array has a name, A, and then it has a number of elements, or a length. And this leads to a contiguously allocated region of memory that is of size n times the size of that data type. So if these were ints, it would be 4 times n in bytes, because ints are 4 bytes each. So let's take a look at some examples. Here's a character array called string that has 12 elements, and you'll notice that each is 1 byte, and they're allocated one right after the other in memory. Here we have an array of ints with 5 elements called val, and of course it takes up 20 bytes in memory from some starting address. A double array, of course the elements are 8 bytes each, but they're always contiguous, okay? Always right next to each other in memory. And of course for pointers we have a difference depending whether we're on a 32-bit or 64-bit architecture. In one case, the pointers are 4 bytes. In the other case, they are 8 bytes, the size of the addresses. Okay, so continuing with this, let's take a look at a little example here. We have a 5-element array called val, and it has the following integers stored in it: 98195. That happens to be the zip code for the University of Washington. Okay, let's take a look at how we might reference these values. We'll start off with an example of val sub 4. So we are actually looking here for the 5th element of the array because the indices start at 0. Okay, so although here we put a 5 for the total number, the actual index of the last element of the array is n-1, val sub 4. And its type, of course, is going to be an int because these are all ints in this array. So the value in this case is going to be the number 5, that last 5 that we see at the address x plus 16. The next example, just using the word val, the name of the array, is going to give us an address to the starting point of the array. So that'll be the value x, wherever we happen to start the array in memory. Val plus 1 is also a pointer. Because val is an address, when we add 1 to it, we do pointer arithmetic. These are of type int, so we will add 4 to x. And so that value is x plus 4. Continuing on, we have the address of the 2nd element of the array, the 2nd index of the array, rather, or the 3rd element, and that would be x plus 8. Okay, again, because we start the indices at 0. Val 5. Now, val 5 is not really in our array. It's outside the bounds of our array. The last index should have been 4. But C doesn't care about that. It'll just do the address computation the same old way and just go to that memory location. So in this case, it'll take the starting address of val, multiply that 5 by 4, and add 20 to that starting address. So it'll really go to whatever memory location is after the end of the array, and who knows what is there. So we have an unknown value. It's totally dependent on whatever is in that memory location. Okay, let's take a look at the next example. We're doing val plus 1 inside the parentheses. That's again that address x plus 4, and then we're dereferencing it with the star operator. So we're saying, what is the value at x plus 4? And of course the value at x plus 4 is the integer 8. And then finally, our last example, val plus I, an arbitrary index. Again, that is multiplied by 4 to yield the address x plus 4 times I. All right, so that's pretty straightforward. Let's take a look at a larger example. Here we've defined 3 arrays with 5 values each. You'll notice that the type of the arrays is this zip dig for zip digit. And that's a type that was defined in C as being an integer array of 5 elements. Okay, so that's just so that we have a shorthand for defining a new data type that then we can just use to declare values. So we have these 3 arrays of 5 elements each. They're represented in memory to look like this. And here I've shown them actually one right after the other. You'll notice that addresses 16, 36, and 56 just following each other in memory. Of course, there's no guarantee that that will actually happen. That's just how I drew out this example. Okay? So let's take a look at some address computations on this array. Here we have a simple C procedure called getDigit. Okay, it takes 2 arguments, an array and the index of the digit we want in that array. So something like UW3 for the 3rd digit of the UW zip code. So the way we go about figuring out what that value is we just take the name of the array and index it with the other parameter, the other argument, z sub dig. In an assembly code, this turns into a very simple expression. You'll notice here that we have just a simple move instruction for doing that. It's moving a value into the register EAX because that will be the return value of this procedure. And what does it return? Well, it's going to do an address computation. It's going to use what is currently an EAX, and we're assuming that's the value of the second parameter digit. It's going to multiply that by 4, so 4 times digit. Okay, and then add that to EDX, which is the value of the first parameter, the address of the first starting address of the array Z. Okay, so that is the address, and then the parentheses around it imply a dereference that we're going to go to that location and get the value there and put it into EAX. Let's take a look at some other examples of accessing these arrays. Let's take a look at UW sub 3. What would we expect that to be? Well, we expect to go to the UW array here, okay, and sub 3 means the 4th element, so it's not the 9, not the 8, not the 1, but it's the second 9 at address 48. Okay, and in fact we can compute that by taking the starting address of the array 36 and adding 4 times 3, the size of an int times the index. Okay, the value there of course is 9, and that is guaranteed to be that value in terms of its organization in memory. Let's try UW6. Now, of course, that is off the end of our array. We don't have a 7-element array. We have a 5-element array. But the address computation proceeds as before. This time we get an address of 60, which happens to have the value 4 in it, but you'll notice that it's really part of the UCB address, the UCB array. And of course, there is no guarantee that that array is in the location that I've shown it to be in. It could have been allocated anywhere in memory. So that's absolutely not a guaranteed result. In fact, any time that we go outside the bounds of the array, we have no guarantees as to what the value will be. Let's do UW minus 1. That's an interesting index, but the address computation just uses it the same way. This time we get an address of 32. The value there is 3 in the CMU zip code array. And again, that is not guaranteed because it's dependent on the arrangement of these in memory. Similarly with CMU 15, we're now going off to a part of memory I haven't even drawn, so who knows what's there. And of course, there is no guarantee. All right, so the thing to remember is that there is no bounce checking in C, and the location of each separate array in memory is not something that is guaranteed by the runtime system. Let's go on to look at a slightly more complex example. In this case, we have a function zd to int, which takes an array of type zip digits and turns it into an integer. So for example, the UW array that had 98195 as the 5 digits would now, if given as an argument to this function, would return the integer 98,195. How do we do that? Well, it's a simple loop that goes and looks at each digit, multiplying it by 10 each time, so that we use the digits as 10,000ths column, thousands column, hundreds column, tens column, and so on. So the way we're going to do that is by getting that first digit and accumulating a result in a variable. So you'll see in the first case, when the loop runs here with I equal to 0, we'll index z sub 0, the first digit, okay, and we will add that to 10 times zi, which initially is also 0. So the result here would be zi equals 9 if we're doing the UW array. Okay. The next time around, of course, we'll multiply this 9 by 10. So it'll be 90 plus the second digit, which will now have the index z sub 1. And we'll see an 8 here. So we'll get 98, right? And then the next time around, it'll be 98 times 10 plus the next digit, which is, of course, a 1 to yield 981. And so on. You get the idea. All right, so how does this look in assembly code? What we see here is that we've had our compiler do one important transformation, actually a couple, but the most significant one is that rather than using this loop index and doing an address computation each time, what it's done is it's taken the starting address of the array and then just adds to that as we go down each element of the array. And by adding 1 using the construct z++ in C to indicate an increment by 1, it's essentially adding 4 each time because they're ints. Okay? And so the other transformation is it's taken our for loop and transformed it into a do loop with the test at the end to see whether we've reached the last address of the array. Okay, so that's our transform C code, and now we can go on to see the actual assembly code that's generated. So I've listed here where the variables are stored in which registers and the computations that need to be done. And you'll notice that the main computation is 10 times a digit plus the next digit. 10 times the current accumulated value plus the next digit. And that's been factored a little bit to look like that instead. And let's see why that's happening. All right, so our first instruction basically just clears a register so it can represent that starting accumulation of our result. Then the next thing we do is compute the end of the array. Since we had a fixed size loop that went around 5 times, we know that the end of the array will be 4 elements down. So we just do z plus 4 as the end of the address. And that gets translated to, of course, 16 because of the size of int. All right, the next thing that we do is start doing some arithmetic to do our computation in the body of the loop. And you'll notice here that first we use an effective address instruction to compute 5 times zi. That's convenient to do because we can do a power of 2 times the value plus the value again, which gives us 5 times the original value. All right, and then we get the value of the next digit by dereferencing the address z. Remember that star z is represented by those parentheses around the value in the register ECX. So it says to dereference that as an address. And then we add those together, but further multiplying that 5 times zi by another 2. And the way we do that is 2 times that value plus the star z, and take that result and put it into EAX. Okay, so we're ready for the next time around the loop. Of course, we then do the test of the loop, comparing whether we're at the last address. And if we are, we continue on. And if we're not, we loop back around to this label L59. All right, so that is the assembly code implementation of this.